So in deep nets, I call them DNNs, deep neural networks. This aspect of generalization has been a very hot topic. As you know, in machine learning, all of us are obsessed with generalization. And so it's a very important topic to think about. And particularly after an important paper came out in the last ICLR, there's been a lot of interest to understand how deep nets generalize, particularly deep nets which are typically tend to be, the powerful deep nets tend to be heavily over-parameterized. So I'll use the word over-parameterized to typically mean the case where the number of parameters in the network is a lot higher than the number of examples that are used for training, right? And so that is the over-parameterized space. And typically, powerful DNNs tend to be very heavily over-parameterized, and they do extremely well in generalization. And people are trying to understand that. So there is a lot of work that's going on in the last 1 year. And I want to take one aspect of that, which talks about the interplay between the optimization method and generalization. Particularly, the stochastic gradient descent methods have shown great performance, right? Everybody uses that in deep nets. And so one would like to understand, what is the connection between stochastic gradient descent and generalization, right? So that's the aspect I'll be focusing on. And that's the interplay. So the interplay also comes in if during the process of understanding that, that understanding, can it lead us to better optimization methods? So you go both ways, right? So that's the part I'm going to be talking about today. So let me just introduce the basic the training process. So you have an error function, which is a summation over examples of the loss terms of individual examples. And then currently I'm not including any kind of regularizer there, because I want to focus on the unregularized case particularly, because that's the interesting part. And you do a weight update where you take the current weight and then move in a certain direction G. And that direction G, it could be either through gradient descent, where you use the entire batch gradient, or you could use the typical way it is done is that people think gradient descent, the batch gradient descent is very slow. And so people go for mini batch stochastic gradient descent, where you choose a batch B and then compute the average gradient over only those examples in the batch, and then make a step and then do many such steps, right? Keep repeating, right? And so this mini batch SGD, I'll just refer to as SGD throughout. And when the batch size turns out to be small, you can see a lot of variance, right? In the different batches will give very, very different directions. And when the batch size becomes larger and goes closer to the batch, that noise reduces. So there is a nice variation of this noise level going from below small batch size to large batch sizes, and that's an important factor actually, right? So when you come into batch gradient descent, one can talk about a variety of methods. One can talk about simple gradient descent. One could use more complex optimization method based on gradients like conjugate gradient or a quasi-Newton BFGS kind of methods also. But I will club them all into the same group, and I'll, as a representative of that class, I'll include any time when you use a very large batch size, maybe as large as the total number of examples itself, and use a simple gradient descent. That's to be some kind of a representative of that class of methods, right? On the more deterministic kind of methods versus the stochastic kind of methods, right? Okay. All right. So here is an interesting plot which comes from one of the Facebook papers where they used a whole bunch of GPUs in parallel to compute the SGD optimization, and they were playing with mini batch size, and the typical observation is that once the mini batch size goes beyond a certain value, you start losing on generalization, right? So here is on the y-axis is the validation error on the ImageNet data set, and so you start doing bad here in this area where You start trying large batch sizes. So it's this sort of a well-known thing in DNNs that large batch sizes tend to be poor, right? And so as a rule, most people don't use even batch methods, right? They try to avoid it, right? So we have to see why this is. So before going into any of that, I want to talk about deep nets and over-parametrization. So just to give some examples. So here is an example where in the y-axis, I plot the number of model parameters. That means I'm varying the size of the network to small to big size networks. And then you fix the number of examples to, let's say, 50,000. And then on the y-axis, you plot the generalization error, the performance on the test set, right? And you can see that, so there are these various plots going on here. This blue line basically tells you the training error, which keeps improving, right, as you throw in more parameters, because you're talking about more powerful networks. At some point, the training error even becomes perfectly zero, right? And so this is, you can think of as the memorization phase kind of thing, right? It doesn't have to be exactly memorization, but it's a combination of pattern finding and memorization. But if you look at generalization, the test set error, right? Test set error also keeps dropping as you make this network big. At some point, like let's say in the area where the number of parameters is roughly same size as number of examples, you start reaching an optimum. But what is more interesting is that as you make the network more and more powerful, you don't see the curve starting to go up, right? Which is what typically you expect with over-parameterized cases. But in DNNs, it tends to remain flat. And there are cases even when it slowly rises also, right? And then after some time, it drops, right? So the over-parameterized region, even without any kind of regularization, so that's the nice part. Without any regularization, you still get very good generalization error. Well, now, why is that, right? That's going to be the main topic I'm going to talk about. So here is another example where P over N tells the ratio of the number of parameters to the number of examples. So you typically say, here is a mildly over-parameterized system. It's roughly in the level of 3. You get a certain test error rate. And as you jack up to much higher ratios, you throw in lots and lots of parameters, you make the network more and more powerful, you start seeing even better generalization, right? That's one I was talking about just now, okay? So why is this happening, right? And here is another real practical case where this chart shows the ImageNet performance historically over the last 6 to 7 years, right? Various cases which have won the competition in various years have been plotted here. And the size of this tells you the number of parameters, right? You can see the sizes given here. So roughly for the number of examples here, which is about 15 million examples, some of these are, sort of in the under-parameterized region. But then as soon as you come to this size, all these are over-parameterized cases. And they tend to do very well, right? So this is another example. So let's talk about over-parameterized system mainly, and the focus is on that, right? In order to understand, let me start with kernel methods to see if you do over-parameterization, what happens in kernel methods. Because kernel methods are much easier to understand because you can think of them as doing linear solutions in a kernel feature space, right? And it's easier to understand. So if you look at kernel methods, you have this very nice theory based on regularization. And this regularization is based on the concept of margin, right, in linear classifiers. And the margin sort of tells us that this regularizer, even though the original kernel feature space may have tremendous flexibility, this margin has a way of controlling that flexibility, right? And the larger the margin, you have the flexibility is controlled. So there is a thing called the VC dimension, which has the margin in the denominator. So the bigger the margin, the VC dimension, which reflects the capacity in the model, which the flexibility, right? That's controlled. And you have some nice theorems that say how the generalization error is controlled by the VC dimension, right? So this theory sort of tells us that using regularization, right, the large margin-based regularization, right, you can, by controlling this regularization parameter lambda, which when you put lambda equal to 0, the regularizer is given tremendous importance. When lambda goes towards infinity, it's the error function that's given more importance, right? And therefore, it has a very, very nice way of controlling the amount of regularization you're doing. And then you have, using which you have very good control over controlling the generalization error, right? Fixing at the right place where you have sufficient flexibility to fit the error terms, and then you also have control on the flexibility, right? So that's what generally works. We know that these methods work very well. But then let's take kernel methods and ask the question: if I remove regularization, right? We know it gives you a sufficient condition based on all that theory, but is it necessary? Can I remove the regularizer altogether and then still get good solutions, right? When I say good solutions or great solutions, I don't mean absolutely optimal solutions, but they give me pretty close to optimal, right? So that kind of thing is what I refer to as good generalization. So consider the following experiment. So I take stochastic gradient descent, right? And then let's take the example of just a simple squared loss so that it's easier to understand. So I'm operating with basically a linear classifier in some space which could be defined by a kernel, right? But for easy representation, let's just call it as if we are operating directly in that space. And you talk about a typical SGD update, right? So this is what I've written here is the mini batch stochastic gradient update, right? So if I start from 0 weights as my initial starting point, right? You can write, because if you look at the expression rewritten here, every time the change you're making to the weight vector is always some kind of linear combination of the input examples, right? And therefore, it's basically the update as well as the weight vector at any point in time is always a linear combination of the training examples, right? And therefore, the final optimum also will have that same property, right? And now what you can do is that you can do, making some assumptions on the matrix of the input vectors, the capital X, to be full rank. You can actually take the final solution. Once I reach the optimal point, which I know will, all the error terms are made to 0, right? So that's what I've written there. And finally, when you write it down, you basically get k alpha equal to y. That's the equation that you want to solve, right? And so that basically corresponds to the case where you have no regularization, right? So that's so I'm just sort of going through, but I'm approaching it from the angle of what SGD will do, right? Instead of deriving this in any different way, all that I'm saying is that I'm approaching it through what SGD will do, okay? So this kernel method with 0 regularization, when I use SGD as my method, it does very well. So for example, on the MNIST data set, the actual SVM trained with in the proper kernel way using regularization and tuning the regularization parameter, it's reported to be 1.4% in there is a MNIST page that is maintained by Jan LeCun. So it states it as 1.4%. And it turns out that this method I just talked about, where there's no regularization, that gives a test error of 1.2%, which is pretty good, right? it's doing even better than an SVM, right? This was done using a logistic regression thing, so there's a slight difference there, but the error rates are very good. So that's the key thing to point out. So the reason why SGD does well, this is the point I want to focus on, right? Why is SGD doing very well even when I don't have any regularization, right? So it turns out that this solution that I talked about in the previous page, it's nothing but the minimum norm solution. In other words, it is the solution of this problem. So in other words, among all solutions which give you zero error, this SGD is going to that optimum that actually minimizes the size of the weight vector, right? So that's what is happening. And we know that minimum norm solution has all these nice robustness properties. It is related to good margin properties and so on, right? Of course, I'm doing here making things a lot simpler by doing only least squares kind of fitting. But then even in other kinds of losses, one could write a more careful theory to say all these things, right? It's pretty much the same thing, right? So that's a very nice wow property of stochastic gradient descent. Even though it was purely an algorithm working without a regularized loss function, the endpoint, the final solution it reaches is having all these nice minimum norm properties and the nice robustness properties, and through which it's regularizing well, right? So you're feeling, oh, there's something magical about SGD, right? But it turns out there is nothing magical about SGD, in this case at least. And you can see that by looking at an example, right? So here is an example where I've taken a case of, let's say, 3 weight variables are there. So you're operating in a 3-dimensional space. And in that 3-dimensional space, I have, let's say, 2 loss terms, right? So essentially, those 2 loss terms will span a planar space, right? And you know that the set of all possible solutions, right, will lie on an orthogonal space onto that X space. So this is the space of all possible solutions, right? And the solution that hits the plane passing through the origin, right? And that turns out to be the minimum norm solution, the one closest to the origin, right? But any point on this line is also a solution, right? But SGD hits this particular solution. Why? That's because it is starting from here, okay? So you started the SGD algorithm from the origin, and therefore it went to the minimum norm solution. If you had started SGD somewhere here, it would have gone to some other point which may not have good robustness properties, okay? So that is one comment. The other comment is that if you go back and look at a couple of slides earlier, we wrote the SGD solution starts from 0 and then keeps on adding linear combinations of the input vectors. And so that property is the one that leads to the optimality for the minimum norm solution, right? That property will hold for any gradient-based method. It doesn't have to be only SGD, right? It could be batch gradient. It could be any kind of gradient-based method, right, which converges. So in essence, what we are trying to show here is that we'll get to that minimum norm solution, which has very good robustness properties, whenever you use any gradient-based method and starting from the origin as my starting point for the weight vector, right? Then you go to the minimum norm solution, which is good, right? But there's nothing special about SGD, so that's the point I'm trying to make. On the other hand, in DNNs, if I look at it, SGD reaching very good generalization properties is something really special, right? And therefore, this kernel method analysis is not showing you that full power of SGD because there's nothing very special about SGD here. But as we go along, the rest of the talk, I want to point out that SGD has some other good properties which are actually making it very special, right? So the kernel analysis doesn't lead much. The other thing to point out is that if you look at the Hessian, which is basically the second order matrix of all partial derivatives of the error function with respect to the weights, right? It's a P by P matrix, where P is the number of parameters, right? That Hessian matrix, if you look at the quadratic error case we had, that matrix is just a constant. So wherever you go in the weight space, that second order Hessian is a constant, right? Even if you go to non-quadratic losses and look at the Hessian, right, the second order properties, they don't vary too much, right? They mildly vary. But it turns out that in DNNs, the variation is quite a bit, which leads to interesting things happening, okay? Which is what I want to get into as a little bit later, yeah, okay? So you just want to point that out here. So that's the kernel analysis. But let's get into really the deep nets, right? First, some basic insights. So you have the error function, again, unregularized form. You have the gradient. You can write expressions for the gradient, Hessian. Still, I'm working with quadratic losses just because my analysis becomes easier. But when you write the second order terms, right, the Hessian terms, you see that it's a summation of two kind of terms, T1 and T2, where T1 is of this form, right? It's basically the gradient vectors multiplied with transpose, right? It's in that form. And there is a term T2 which is fundamentally second order in nature, right? And this combination turns out to be very important in deep nets, right? For example, if you look at, so one thing to immediately see is that if you look at the T1 term here, right, there are basically n outer product kind of terms, right? And therefore, when you're talking about the over-parameterized case, when you have a lot more parameters, the rank of this matrix is determined by the number of examples, right? So if you're, for example, if you're looking at 50,000 examples in 1 million feature space, parameter space, it can have a rank of only 50,000, right? And therefore, you have a lot of, this is a rank deficient situation, right? If you look at only T1. On the other hand, T2 can make depending on how nonlinear heavy is the deep net error function, that can lead to a fuller kind of Hessian. When I say fuller, it means that it is sharply varying in all directions, right? So this term can make you a lot more sharper behaving, whereas this term has a tremendous amount of redundancy. In other words, there are certain directions in which it's sharply behaving, and on a large bunch of other directions, it is just flat, right? So that's the way the Hessian is organized. So for example, if I look at local minima, right? If I have deep nets having local minima and global minima, at local minima, where particularly if you look at bad local minima, which is the case where the error value, the total error value turns out to be large, right? So when the EIs are large, right, then this term sort of starts dominating, and therefore this term is quite significant, and therefore it turns out that local minima, which are bad local minima, tend to have very sharp curvatures around them. And therefore, because of the sharpness, and because you're having noise present in the whole stochastic dynamic system, right? The possibility of getting caught in those very sharp varying local minimas is very low. So you get thrown out of that very easily, right? You don't get back and caught on it. On the other hand, the global minima, right? And because you're talking about a severely over-parameterized, overfitting kind of system, the possibility of, like we pointed out in one of the earlier graphs, as you throw in more parameters, the training error becomes 0, right? So it goes 0 or close to 0. And therefore, when you're talking about global minima where all the EIs are being zeroed out very nicely, right? And the EIs, when they go very close to 0, these terms die out, right? And therefore, it gets dominated by, the Hessian tends to be dominated by T1 kind of terms. And so you're talking about very flat kind of behaviors. And the chances of going to those global minima is a lot higher, okay? And that's one of the reasons why you see in deep nets, people generally don't worry about getting caught in local minima, because that typically doesn't happen. It's your bad luck a few times, but typically you restart from a different initial starting point. You're pretty much guaranteed to go towards the global minimum, right? And then one thing to note is that because of the severe non-convexity, nonlinear nature of deep nets, there are just numerous of these global minimums, right? It's some people, it's tried to estimate it, but it turns out it's just so numerous, it is not worth talking about, right? You can go into any one of those global minimas depending on, where you start your weight vectors from, okay? So these are some things to be aware of. Okay, so this is what I just talked about. Getting to a global minimum is easy because of these various properties, right? You don't have difficulties reaching a global minimum. Okay, so this is what is actually the way the weight space is structured. So in the weight space, what happens is that there are all these various global minimas. I've just put 3 of them, but like I said, the number is just so numerous. And then depending on where you start, it will go to one of those global minimum. There is a basin of attraction for each one of those global minimas, right? And this global minimas, let me look at one special case, right? Where suppose, the global minima is such that all error terms are zeroed out perfectly, right? Zero training error, right? When you look at that kind of a case, then that set of local minimas, if you look at it, all the error terms equal to 0. That means E1, E2 up to En equal to 0. So you're really talking about n nonlinear equations in P unknowns, right? And we know P is very high and N is small. And therefore, you're really talking about a nonlinear manifold of very high dimension, right? The dimension of that nonlinear manifold is P minus N. Right? This is very, very much like linear algebra, but it's happening in a nonlinear manifold setting. Okay? So, for example, if it's 100,000 parameters in 25,000 examples, the difference 75,000. That is the dimension of that nonlinear manifold. Okay? So there is a whole set of connected global minimas, right? But in reality, because of noise being present. For example, the same example may have 2 different labels given to it, right? That's noise. So whenever you have noise, you may not be able to perfectly zero out all the error values. So there'll be some noisy things. But when you look at in that setting, if you look at, so there what you have to analyze is, look around, the global minima and look at, let's say a region around the local minima where the error is very, very small, right? So that region also tends to be having a similar structure, right? With lots of kinks, but then it is having a similar structure. In other words, there is a whole range of in certain dimensions, right? Large number of dimensions. There's a nonlinear connected set of things which are forming a low error region, right? And because of the highly nonlinear nature of things, different points in that low error region are having different Hessian properties, right? In some places, the curvature may be very high, and then in some places, the curvature may be flat. All kinds of things are going on with these deep nets because of the complex networks you're looking at, right? So we need to be aware of these things. And these are going to be, very crucial for understanding performance SGD, right? So let's come to an empirical analysis of SGD. And so here is an example where, again, I simply just pulled out an example to point out that if you're using a large batch versus a small batch, there is a, considerable difference in generalization error between the two. Okay, so small batch tends to do well, right? This is just giving another example, right? Now, here is the crucial thing. So this was from a last ICLR paper. The main point this paper tries to make is that the generalization of a particular weight vector that you end up, right, is very closely correlated with an idea called sharpness. So which is basically how rapidly the error function changes around that particular point, right? So here is one definition. So of definition of sharpness, all that you're doing is that you're looking at some kind of a neighborhood of a particular weight vector, right? In each dimension, you move a relative epsilon movement in each direction, right? That defines a rectanguloid in the weight space. And in that, you see what is the maximum error that you can get, right, in a relative sense. And that sort of defines an idea of sharpness, okay? This is just one definition of sharpness. There are a lot of people who, sort of criticize why this sharpness is bad. But in this paper, they defined this as the sharpness. And what they found was, when you look at, when you vary the batch size of the stochastic gradient, and then drew the testing accuracy you got, right? And you can see the red plot being the sharpness value that is measured, right? And so over batch, as you increase batch size, the sharpness becomes higher and higher. In other words, if you use a larger batch size, you tend to go to weight vectors in that global minima space where they tend to be sharp. And if you use smaller batch sizes, you tend to be finally located in weight vectors that are less sharp, okay? And then the generalization error, if you plot, the generalization accuracy, sorry, in this case, accuracy is higher the better, the blue line, and that tends to be perfectly negatively correlated with this idea of sharpness. So in other words, the sharper you are in a particular weight vector that you reach, that's bad news for you. You're losing on generalization. If you are at a point where things are a lot flatter, right? So sharpness takes very low value, then there the accuracy is a lot better, right? So there is a very good correlation between the two. So that's one of the key things that was pointed on the paper, and there's been a lot of discussion around that. And why this happens is sort of clear, right? So here is an example which says that, hey, there is a flat minimum there, and there is, think of a sharp minimum here. And when you study test error, right? So this training error curve is something which you're optimizing. And the test error is what you're really interested in for generalization error, which is you can think of it as a shifted version of the error on the training set, right? So these dotted lines denote the shifted version. And therefore, on a sharp minimum, when you do the shifting, at this point, if you look at what is the value you'll get from the dotted line, it's a lot higher. Whereas here, if in flat places, if I look at the difference between the two, it'll be a lot less, right? So you prefer flat regions. So flat regions mean better generalization, right? So that's sort of easy to see. But then the question comes, the real question is, why does mini batch SGD with smaller batch sizes go to the flatter places, whereas the large batch sizes or batch type methods, why do they go to sharper places, right? So that's the question that needs to be answered. It's not very difficult to see. And to analyze that, you approach it through what is called as a Langevin. It's a well-known differential equation in physics. What you do is that this is the mini batch gradient, and this is the update. And what you do is that you rewrite it as, you take the mini batch gradient and write it as the full gradient minus the difference, right? So you write it like that. So where G is the full gradient. And therefore, you can write the Langevin system, right? So here is what I've written as the Langevin system. You can write it as operating it with full gradient, to which a noise is added, right? And that noise turns out to have, because of you're taking difference of two means in the large analysis, central limit theorem kind of analysis. It turns out that you can treat it as a Gaussian with zero mean, and with a certain variance, which is of this type, where if the batch size tends to close to the full batch size, then the noise is pretty much zero. That means this becomes pretty much a deterministic kind of method. And the smaller b is, the larger is the noise here, right? And it tends to throw things a lot more around, right? So you can think of SGD with very small batch size being jumpy all over the place, whereas the other one is a lot more deterministic. Now, if you analyze this differential equation, right, the Langevin system, treating this to be Gaussian, right, so that the analysis becomes simpler, it turns out that the steady state distribution of that comes out to be a Boltzmann distribution, which is determined by the error function, right, and also with the variance appearing in the denominator, right. So if the variance is very large, you can think of it like annealing taking place with high temperature. That means things are jumping around a lot. When the variance is very, very small, that means that you're going towards the zero temperature, and then things are quickly trying to converge whatever is the nearby optimum and so on, right? It's more deterministic, right? So that's what is happening. Now, that means that what it says is that the amount of noise you give, right, that tells you what kind of distribution you'll get in the weight space when you operate with stochastic gradient. So here is a very simple experiment where you take a 2D example of two weights, and then you purposely make one global minimum which is very sharp here, and another connected set of global minimums which are sort of shallow there, sort of flattish. And then you do a simulation of the Langevin equation, and then you look at, draw a histogram of, in the weight space, how often SGD will go and, or a Langevin solution will end up in those points. It turns out that even though the error values at this flat region and this sharp region both tend to be the same, right? They're very small, but still, in terms of the histograms you get, that sharp point has very few points going and lying in them, whereas the huge bulk of weights go to the other flat region, right? So that's what is happening with SGD. Because of the noise present, it is going towards flatter regions, right? And that's the magic of SGD. And if it, that's the point. I'll come back to the same figure. So it turns out that in the end phase, so there are two phases of the SGD. One is it takes you from a starting point. There are many, many, many global minimas, right? Depending on where you start, it's going to one of those global minimas. And once it gets into the basin of attraction, right, then there is a second phase where the noise is sort of going to these low error regions. But as I said, the low error region itself is a large region of possibilities with different properties in different places of sharpness, and it is going towards places, or pulled more possibly towards places where the function is error function is a lot more flat, and the process generalizing well, right? So that's what is happening. So some conjectures here, which this is something that I sort of expect more and more results to come in the near future, is that depending on your starting point, I said you may go to any one of these global minimas, right? But then people have generally observed that the starting point really is not too immaterial, right? It's depending on wherever you start, you still end up in good solutions. So that really is meaning that all these global minimas are probably equally powerful, and they all have their own flat regions. And so which basin you go to, right, doesn't seem to matter, okay? So you seem to do well, right? So, but that's again, conjecture that needs to be proved. And then, of course, After that, you know, they move to the flat regions, right? Within one global minimum, right? But the precise way you have discovered, you have tried to explain it through some Langevin kind of analysis, but I think you need to give a lot more precise answers, right? These are expected. So one of the things is that we defined one notion of flatness, but then that doesn't mean that that's the end. There's a lot of discussion around these things. So I expect to see a lot more set of results coming in the near future, which tries to nail down what this flatness means, and whether you can, using that flatness, you can give nicely connected by theory to generalization. So it turns out it's all coming to, just like margin is solution dependent way of controlling generalization. It is all coming to, for DNNs, it turns out that flatness is the corresponding thing. But how that has to be defined, has to come through, right? So another direction people are taking is that, yeah. Okay, yeah. So one other direction I want to mention is that people are asking, hey, can I go and modify my objective function, the error function, so that this concept of flatness is included into that definition, right? So that is something that's going on. There is one measure that tries to, average out the error measure in all directions, right? That's one effort that's going on. That's shown to already improve results. But then all these still need to be nailed down properly, okay? So let me skip many of these. There's a lot of things in the theory which I'm trying to connect to sensitivity. There is a very good set of recent results on information theoretic approaches, but then it's still controversial because there is this work of Tishby's group which got a lot of popularity in the last several months, right? But then a recent paper that has been submitted to ICLR is contradicting all that work, and so there's still under very fluid currently. But this plot is very interesting in the sense that during the SGD progress in the epochs, there are two phases. One phase where it is going towards a global minimum, one particular global minimum, where the weights are large in size, but the noise is very low. But then there is another region with the two switch in places. The weights go and to settle in small values, and the noise sort of takes over, right? Sorry, I forgot to say, it's not weights, it is the gradient sizes, okay? The gradient sizes. So because as you go closer to optima, the gradient sizes start becoming very small, right? So that's why they start from big values and then start going to small values. By the way, these are all in log scale. And this is where the noise sort of takes over and the Langevin sort of kicks in. Right, let me skip all this. Yeah, so summary I can skip. So just the final comments. So it is a good feeling that SGD is working well because of these things happening. These are rough explanations, but then SGD itself is not really designed to go towards flat regions. It's just that they turn out to go to flat regions because of some nice things happening. So one should not remain satisfied just by knowing this, but really you need to go to understand various things. How do global minima, structure, how are they, what are the properties of the nearby error regions, what precisely cause generalization, a precise definition of flatness, right? These are all things that need to be really nailed out in the coming years, I think. So a lot of exciting things you can expect. So through that, you may probably expect improved SGD methods, maybe even to the point of even batch methods with appropriate the definition of the objective function can be made to go towards flat regions, right? All these things you can sort of expect to happen, right, in this whole area, right? So you are bound to see some exciting developments in optimization, right, going forward. So that's pretty much it. Any questions?
So we do have time for one or two questions, if, well, Clément.
Thank you. Thank you for the talk. I was wondering, because when you look at this Langevin equation, for the variance of the Boltzmann distribution to be like big enough. Actually, you're speaking about SGD where you don't have decaying step size. And so in some sense, you do advocate using SGD with constant step size in opposition to the convex setting where it's not to converge, right?
Towards the end, you always do the decaying, right? So there is a decaying always used in SGD, but those are the rate at which you do that, so that in the crucial phase where you go to the flat region, so that the step size are still large enough, that is crucial.
Yeah, because
right?
if you do this decay too fast, the variance of the
if you do it too
Boltzmann...
fast, then you'll not do. Yeah, so that's crucial. So that's what I'm saying. The real understanding of when how fast you decay and do all that in order to really go towards better generalization, right? That is still needed. I mean, more research is needed. Yeah.
Thank you.
Yeah.
Thanks. So you said that finding flatter proxies for the error function is interesting. Could this be achieved by tempering, for example? Is this a direction?
By tempering?
Yeah, tempering the error function. And look at.
Okay, so what is tempering? I don't. Is it one of the statistical physics terms?
Well, like you would do, for example, in tempering MCMC, where you would actually take the target function with an exponent, and this exponent would vary between 0 and infinity, typically, so that you could find actually solutions adapted to versions of the target,
so
and then mixing.
That.
Yeah, exactly.
Okay. Yeah, I mean, if there are good ways, I mean, that's always. It's similar to what I said for his question also, is that I think one has to come up with good ways of doing that. Yeah. Both empirical as well as theoretical. Yeah. All these will help. Yeah.
So wait, so
I'm interested in the connection. Sorry, I'm interested in the connection between this and Bayesian approaches, both the Laplace approximation and stochastic gradient Langevin dynamics with the Welling and Ter paper. Do you have any comment on that?
Wow. I'm not familiar with those, but you said Bayesian Laplace? But so I'm trying to see the connection between Bayesian Laplace and this one.
So it actually connects to Clement's topic that as I understand the algorithm, they don't reduce the step size, so they keep moving around the that area, so which I think is doing something to exploring the because you're saying the likelihood function's flat, so you're exploring that flat region.
Right.
And again, with the Laplace approximation, you're fitting a Gaussian into the mode. And I'm wondering if your argument kind of connects, say, how EP might be better and different to the Laplace approximation, where the fit is different. Because you're talking about changing the optimization problem.
Yes.
And we already have changes in the sense of we're fitting bounds.
Right.
So seems like there's connections across these things.
That's correct. So all these is pointing to there is probably nothing holy in trying to go to the point which has the global minimum, but rather in the low error region, which is a lot of space for you to try with various differing properties at different places, go to the right place which has the best generalization or the best flatness properties, right? I think that is the key. So how to actually formally state that and change your training formalisms and so, I mean, that is all, I mean, we have to see in the future, more research. Yeah. By the way, all these are very recent works, maybe happening the last 6 to 8 months, and it's a lot of movement here, so you can expect some good things to happen. Yeah.
maybe the last question. You have a question? Yeah.
So I'm wondering about this flatness, sharpness explanation to generalization, because it's not very obvious to me why I should be thinking about the test loss to be a shifted version of the training loss. It seems to me that like classical theory would give me an L infinity bound around the training loss, and that wouldn't say anything about whether sharp minima are better or worse than non-sharp minima.
Correct. So this whole definition of sharpness, flatness is still in the air. For example, after the Kesker paper where I was showing some sharpness results, right? There was this very nice thing pointed out by Bengio's group, which said that if you take ReLU networks, if ReLU is, it's constant 0, and then there is a sharp thing there after that, right? If I increase the scale of the weights coming to a particular neuron by a certain alpha, and then downgrade the weights of the neurons going out, the weights going out, right, by downward by alpha, right? You don't change the overall function, but then that changes the sharpness properties, right? And therefore, what is the definition of sharpness is still, I think, very much in the air, and they are trying to, give some reasonable definition, but you can use that to give sufficiency theory, but to give a proper, necessary, and sufficient conditions. Hey, here is the flatness measure that will connect to generalization in a equivalent manner, right? That is still open, yeah. So these are all, I would say, very rough kind of pointers, yeah.
It's the very last remark.
Yeah.
I had the same remark than my colleague here.
Yeah.
So this is a correlation between so generalization as you're defining on the test set and the sharpness that is some kind of estimated over the training error that we are making. So the thing is that are there any works that trying to define the sharpness over a validation set when we are so to find some kind of correlation between what's going on the training error and any validation error?
But then how do you define flatness even if you have a validation measure, right? That's, I don't think there is anything cleanly you can say it right away.
Yes, because right now you're defining flatness over the training error.
That's right, yeah. And the other couple of slides that I skipped was related to sensitivity of the input to the output. So the weights don't come in. So a lot of people criticize the use of weights in the flatness measure because weights are intermediate quantities that come by, and then the various reparameterization of the weights will do the same thing, like the example I was just giving. And therefore, instead of looking at the weights, why don't you directly look at the input-output sensitivity and then bring that in and talk about relating to that with generalization. Interestingly, there was a very early paper in the early 90s given by Chris Bishop showing that data augmentation with noisy examples equivalent to this input-output sensitivity reduction, which is called the Tikhonov regularization, right? And so it'll be nice if people can connect all these things and lead to some good regularizers and modifying the objective function, yeah. But validation set, how to do it, I still don't know right now.
Okay, thanks.
Yeah.
So thanks again, Keerthi.